Hello there. Today we're going to talk about special purpose diodes. These diodes are a lot more interesting than the diodes we've looked at so far. The diodes we've looked at so far, the applications we've used them in are primarily for controlling current going in only one direction to make rectifiers, turning AC power into DC and things like that. These diodes are used in voltage regulators, in RF applications, and voltage controlled oscillators and things like that. So there's a lot of different types of diodes other than what we've looked at so far. So that's what we're going to be talking about today. We start out with this Zener diode. And the Zener diode is used for voltage regulation primarily. It's operated reverse biased, okay? So the cathode anode here, the positive terminal of the supply is connected to the cathode, which results in a breakdown region here. All right, this is where they're operated. Now the forward characteristic is exactly like a regular diode. So you're going to get 0.6 or 0.7 volts, 0.6 or 0.7 volts in the forward region. But the reverse breakdown is where this thing operates, okay? See if I can get my screen to work here. The impedance, if you notice, go back here, this curve isn't perfectly vertical, okay? So there's a slight slant to it, and that represents a resistance. There's a proportion between current and voltage, which is a resistance. And that Zener impedance, we call it, impedance is a complex resistance, right? It's got some capacitance and some inductance going along with it. Not so much with the Zener diode, particularly when we're operating at low frequencies. All you have to worry about is resistance. But it is indeed delta's V over delta I. Okay, so the change in voltage versus the change in current. As you increase the voltage through, or the voltage or current through the diode, I should say, the voltage, the Zener voltage will change. Okay, it's not a perfect, it's not a perfectly vertical curve right here, right? So as you increase the current, this voltage is going to go up a little bit, or more negative in this case. Okay. So the example that they have here is the Zener voltage changes from 4.79 to 4.94 volts when the current changes from 5 milliamps to 10 milliamps. So what's the Zener impedance? Well, delta V over delta I is going to be 0.15 volts, right? 4.79 to 4.94, that's 150 millivolts, divided by 5 milliamps, and that's the change. So we're going to get 30 ohms, okay? Doesn't change very much when you think about it. We're doubling the current, right? But the voltage only changes by 150 millivolts. That's pretty good regulation, and that's why these are used in voltage regulators. Now, the one thing that Zener diodes do have is a temperature coefficient. They are somewhat temperature sensitive, all right? So there's a temperature coefficient, which is the delta voltage, okay, times delta T, the change in temperature, divided by the nominal Zener voltage, okay? So that's the temperature coefficient. You can also express it as delta V over delta T. So the change in Zener voltage divided by the change of temperature. This is more common down here, this type of temperature coefficient expression, which is in millivolts per degree C. That's what I'm sort of used to, okay? So I think we do an example here. And they can be, yeah, they can be either positive or negative. In other words, as the temperature goes up, the Zener voltage can go up, or it can go down. Okay, so it can go either way. This example here is a 1 in 756, is 8.2 volt Zener, and that's at 25 degrees C. That's room temperature. Positive temperature coefficient of 5.4 millivolts per degree C. What's the output voltage as temperature rises to 50? Okay. Well, at 25, it's 8.2 volts. 50 degrees C is twice that, right? So we're going to go 5.4 millivolts times 25 degrees C. That's the delta T. 189 millivolts is the change in Zener voltage. So you add that to the 8.2 volts, and you get 8.389 volts. Still pretty good. It's still very close to its nominal Zener voltage. 50 degrees C is pretty hot, though. All right, that's that's well over 100 degrees, 130 some odd degrees Fahrenheit. And here's a good application for a Zener, although it's a little less common than the next slide we'll look at. This is a voltage regulator. Again, it's a 756, it's 8.2 volts. The equation here, which you're going to want to pay attention to, is a little Kirchhoff voltage law thing, where you take the input voltage, subtract the Zener voltage, and divide it by the resistance to get the current. Now, all Zeners have a current that they operate at, all right, where the knee starts to happen, right? So this one, they're running it at 9.8 milliamps. That's 18 volts minus 8.2 volts divided by 1K right here, all right? Now, they put a load on here, all right, and use this as a voltage regulator. This is not real common because you can't get a whole lot of current out of this thing, all right, before the Zener you start to starve the Zener. But that's what this equation here is all about. The maximum load current is going to be your voltage divided by this current. As soon as you start drawing more current out of here, you start starving this branch, the load branch starts starving current from the Zener, and you lose regulation. So they say, based on this equation, you can put 837 ohms out here as a load. Not a very big load. That's why this isn't used too often as a voltage regulator. On an internal circuit, however, internal to a voltage regulator, this is exactly how they do it. And that is on the next slide. Yeah, these 3 terminal regulators. We get into voltage regulators in I think in integrated circuits in the spring, 2325, EET-1141C. And voltage regulators are normally 3 terminal devices. They have Zener references in them. That's what this is. It's a Zener reference. So this voltage going into this error amplifier, that's what it's called, stays fairly constant, regardless of what's coming in this input voltage. This error amplifier compares this reference to really what the output is through this feedback element, which is a voltage divider, a couple resistors. It compares these two things, these 2 voltages, and then controls this control element, which is a pass transistor. Basically, it turns a transistor on or off a little bit more or a little bit less, depending on how much current is required out here to maintain this voltage, okay? So you don't necessarily have to know a whole lot about voltage regulators right now, but you do need to know that Zeners are used in them as the reference, okay? And these Zeners are pretty specialized. Some of them are temperature compensated, so to provide more accuracy over temperature. I think they always are in voltage regulators. There's some special techniques they use to control the temperatures of them, or maintain temperature, I should say. Now, putting Zeners back to back like this in this schematic, you can make a limiter or a clamper. So here's an AC waveform, and you notice it's cut off right here at the positive end and the negative end. The voltage that it cuts off at, or clamps at, or limits to, is the Zener voltage plus 0.7 volts. So one diode is forward biased, the other diode is back biased, okay? The Zener diode that's back biased, reverse biased, is producing or limiting to its Zener voltage. The diode that is forward biased is 0.7 volts drop. So it's VZ plus 0.7 and VZ minus 0.7, depending on which side of the cycle you're on here, okay? So this example, if it's a 5.6 volt Zener, you get 5.6 volts plus or minus 0.7 volts, which is 6.3 volts. Okay. And you can kind of turn a sine wave into a square wave this way, a crude way of doing it. It's not a very good square wave, obviously, because it's got these slopey sides, but that's what we do. Now we'll get into some RF stuff, radio frequency stuff. We study this in RF communications. Varactor diodes, they are operated reverse bias also, just like the Zener, except they're used as variable capacitors, voltage-controlled capacitors. Okay, so depending on how much reverse bias you put on them will determine their capacitance. And this is an interesting little picture here. This is a regular PN junction diode, right? And each side of the junction is a plate of the capacitor with a depletion area, which is in the middle here, as the dielectric. So it's a nice model. So as you increase the depletion range, right, that basically essentially moves the plates further apart for a regular capacitor. When you do that, the capacitance goes down. Okay. So if you increase the voltage, the capacitance is going to be reduced. Okay. I think there's a diode or here. Yeah, here's a curve. All right. So here's where we're increasing the reverse voltage and the capacitance goes down. So this is capacitance in picofarad over here, and this is reverse bias here. So when you put a varactor diode, and here's a data sheet. There's capacitance ratio, which is the voltage versus capacitance versus reverse voltage. But there's some other things here. This is power numbers, maximum forward current, maximum reverse voltage, and things like that. I think there's a schematic here. Yeah, okay. So here's the schematic, a schematic of a little resonant circuit. So there's a tank circuit here. This is the Zener diode, or not, I'm sorry, the varactor diode. And here's an inductor. And anytime you put capacitors in parallel, as you see here, with an inductor, what do you get? You get a tank circuit. It's a resonant circuit. Well, this particular quote-unquote capacitor is a varactor diode, and it changes its capacitance based on reverse bias. And it's reverse bias through this resistor and resistor potentiometer here. And here's the bias voltage. So you get the positive terminal on the cathode of the varactor diode, so therefore it's reverse biased. Now, as you change this resistance of R2, it changes the bias voltage on the varactor diode, therefore changing the resonant frequency. So you basically have a variable voltage-controlled resonant circuit. Okay, and there's let's see, here, let me go back. Now there's a circuit, a component called a voltage-controlled oscillator, which again, we get into this in RF communications. Voltage-controlled oscillator, where these circuits with varactor diodes are used in them to create frequencies, oscillate. The output of an oscillator is an oscillating frequency, and there's a voltage input to it that you can control the frequency of that oscillation with a voltage. Okay, and VCOs, voltage controlled oscillators, are used everywhere. They're used in phase lock loops, which we look at later, and all sorts of tuned circuit applications. Everybody's familiar with LEDs, right? LEDs are everywhere. And it says down here, obviously this is dated. Even automobile headlamps may use LEDs in the future. I think a lot of cars have LED headlights now. It seems everything's going to LEDs. It's a huge industry. They say that LEDs will never burn out. That's almost true. They do degrade over time, but not much. What usually burns out you know, in your LED light bulbs and things like that is the driver, the thing that's actually driving the LED, which is usually some sort of a field effect transistor circuit or transistor circuit. That's the thing that goes out. The LEDs are perfectly okay, but the stuff that's feeding it, they die, unfortunately. So not a perfect world. And LEDs are getting very high intensity and very high energy nowadays, as pretty much everybody knows that. I think you can get them. LED flashlights, pretty common now. Most LEDs emit a specific range of wavelengths, all different kinds of colors. Green LEDs, this particular one they have down is 540 nanometers. You can find them in any different color now. Matter of fact, you can find LEDs that are red, green, blue LEDs that can produce almost any color. They have multi-terminal, obviously, one common and then 3 other leads on the LED, so it's a 4-lead LED that one controls the blue, one controls the green, one controls the red LED in it, so it's a triple LED. And you can also get dual LEDs. And of course, there's viewing angles, how directional they are. That depends mostly on the lens that's on the LED. And LEDs, there's a lot of different packages. Some are leaded, some are surface mount, meaning they go right on the circuit board without any leads. Now, one interesting thing about LEDs is you know, the forward voltage drop of our regular diodes is about 0.7 volts. You're not going to find an LED with a 0.7 volt voltage drop. They're going to range from about 1.2 volts, this is 1.5 volts here, but in reality it's 1.2 volts to over 3 volts. White LEDs tend to be pretty high voltage, forward voltage drop. The green ones are down 1.2 volts, 1.5 volts. Red's a little higher, maybe a little less. It depends. You look at the data sheet, you'll see what the voltage drop. So here's a red, bright red. Oh yeah, and the different brightnesses too. The brighter it is, usually the higher voltage drop it is. So this one, here's an example, bright red LED, 2.2 volts at 20 milliamps. Yeah, LEDs run 10 to 20 milliamps usually. Your you know, general purpose LEDs, indicator LEDs. Certainly some of the high power ones, the high intensity ones can go well into the amps, many amps of current. So this example here has 2.2 volts, 20 milliamps. They're running it from 5 volts. So the circuit is 5 volts minus 2.2 volts divided by 20 milliamps. So you're going to want a 180 ohm series resistor, all right, to limit the current. You can't just connect up, like for example, 2.2 volts is what the voltage drop is. You just can't take 2.2 volts and hook it up to the LED because there's no way of limiting the current. So you have to limit the current in the LED. One side exercise that you can do is this 180 ohm resistor. What wattage does it need to be? All right. Well, watts is what? Power. Power is what? Voltage times current. Right? Or what else? V squared over R, or I squared times R. So you can take 20 milliamps squared times 180 ohms. That's the power going through this resistor. All right. So you can determine what wattage resistor that needs to be. Maximum power dissipation. Here's 20 milliamps, 2.2 volts, 44 milliwatts. That's the power that's dissipated by the LED at that point in time. That's not the power in the resistor that we just talked about. That's the power in the LED. Now that's LEDs. Now photodiodes works the other way. Okay, in other words, it doesn't emit light; it takes light in, and it's a exposed junction. And whenever you have an exposed junction, you bombard it with photons. What that does is it changes the depletion region and will change the amount of current that is able to pass through the diode in reverse bias. Okay, again, these are reverse bias. So there's a small amount of current when there's no light, that's the dark current, and then as you increase the irradiance, the amount of light, current starts to flow. It's a photosensor, right? You walk into a 7-Eleven, ding ding, at the door, you're interrupting a photosensor. That's basically what these are used for. We have laser diodes. They're like LEDs, except that the light coming out of them is much more narrow in spectrum. In fact, a laser ideally produces what's called monochromatic light. It really is only one wavelength. Laser diodes are used in DVD players. Remember CD players? That's where they were first mostly used. But DVD players, DVD, Blu-ray players, and things like that, where the laser hits the disc and bounces off and gets picked up by a detector, a photodiode, in fact, and those oscillations are ones and zeros, representing data of your movie or music or whatever. Laser pointers, fiber optic transmitters. That's a good application for them too. Barcode readers at the supermarket, or Lowe's or Home Depot or wherever you go. All right. Okay, Schottky diodes is the next kind of diode. These are really common. These are great diodes. Why do I say that? Because they've got a really low forward voltage drop and they're really fast, meaning that this metal silicon junction here is very thin. Okay, they haven't got a very good low reverse rating, but that's not really where they're operated. They do clamp. Are used in clamping circuits for voltage regulators, or steering currents in voltage regulators and switching voltage regulators primarily. But these are very common diodes, are used a lot. The thing to remember about Schottky diodes, it's got a really low forward voltage drop and very high, which means it's highly efficient. You don't get that 0.7 volt drop. It could be a 0.1 volt, 0.2 volts. That's it for a Schottky diode. Okay. A pin diode is another diode that's sometimes used in resonant circuits or filters, a voltage controlled filter, because it's basically a voltage controlled resistor. Okay, it's got this intrinsic region in the middle, and it's a 3-layer diode with another little intrinsic region in here, which what that does is when you bias it, okay, the voltage that you bias it with will determine its resistance, much more so than a much more dramatic curve than a Zener diode. I guess that's the big difference between a pin diode and a Zener diode, is that its resistance with voltage is much more extreme, and therefore you can make voltage controlled filters. You can just use basically an RC filter. 1 over 2 pi RC. Remember that formula for a filter, high pass filter, low pass filter. You can put a pin diode in there as part of the circuit and control that filter, the filter characteristic, the cutoff frequency, with a voltage. So voltage controlled filter. Here's a fun diode, a tunnel diode. This is used in a lot of RF circuits. Notice there's a negative resistance region right here, and then it bottoms out, and then it starts going back up again. Well, it turns out that point C here is the point of lowest resistance, Okay, so therefore you can put it in a resonance circuit, and at that particular voltage and current point, it's going to have its lowest resistance and therefore likely resonate at that point. Okay, and that's why these are used in oscillator circuits at microwave frequencies. And I don't know if they're used in microwave ovens, but they are used in RF transmitters for the transmission oscillator. Okay, worked at very high frequencies. I actually made, when I was much younger, doing hobby stuff, I made a tunnel diode radio, just a receiver, and it used this oscillation point as for part of the local oscillator. Let's see what else we got here. Current regulator diode, pretty specialized diode. We don't use these too much. I don't really come across them very much in my work. So we'll kind of blow past that. Here's some diode symbols. You should become familiar with these, particularly the Zener. Notice the Zener has a little bit of, has these little slants on the cathode part. Light emitting has diode has a couple of arrows coming out of it, showing the light coming out, and then a photodiode has the arrows going into it. Varactor diode, sort of a diode capacitor combination, so that's a good symbol, right? Laser diode, same symbol as light emitting. Schottky diode has these little square ends on it, okay? Pin diode doesn't get its own symbol, it's just a regular diode symbol. And a tunnel diode has these, both of them going, both the little ears on the cathode going back, and the current regular diode looks like a current, okay? Current source. And here's some terms. Zener diode, you should look at these, designed for limiting voltage across its terminals. Varactor variable capacitor diode, LED. Electroluminescence is a process of releasing light energy by recombination of electrons in a semiconductor. Okay. Pixel, basic unit for producing colored light. Photodiode, diode in which reverse current varies directly with the amount of light. And light amplification by stimulated emission of radiation. That's what laser stands for. And there's a little quiz at the end here, so you all should, you have the PDF or the PPT, should probably go through this on your own. This quiz. Okay, that's it for this week, and we will talk to you soon. Use the discussion space if you have any questions, and you're turning in assignments and labs pretty consistently, so thanks for that. Keep working hard, and above everything else, stay healthy. Thanks.